Are there any questions before I get started here? Mm-hmm. What is dy over dx? Uh-huh. Sure. Let's see if I can find it here. Let's see here. Trying to see if I can find which problem had that. Or that's just a generic question. Uh-huh. Sure. I don't. Again, that doesn't. No, it doesn't matter there or not. That's a fair question, but let's see here. So the derivative, right? We defined for a function, right? So if we have function from some subset of the reals, and it's real valued, right? If you have a function and you have a point a in the domain of the function, then we say f prime of a is the derivative of f at a, provided the following limit exists, right? The limit below exists. So f prime of a is the limit as h goes to 0 of f of a plus h minus f of a, all divided by h. Right? Now, so that's like when you that's the formula for like the derivative when you're trying to find it. This is the formula for the derivative at a. Now, we have another formula. We could also write that the limit as x goes to a of f of x minus f of a over x minus a. So that's an alternative way you can calculate the derivative. So you can use both, or is like one used for like a specific? You can use either one. It makes the algebra work out different. So it's like a question of convenience. Okay. Sometimes the algebra is easier to see using the h limit. Sometimes the algebra is easier to see using the x limit. I don't have a strong preference one way or the other. Generally speaking, when I'm writing a homework solution, if I find myself having written like 3 problems using the h limit, I'll try to switch over to the x limit to give you, more diversity and like how you're looking at it. Okay, so all of this said, the function a maps to f prime of a is the derivative function. Which we just call f prime, all right? Now, when when y is equal to f of x, all right, then we have dy dx equals to d dx of f of x. And that's another notation for f prime of x. right? And going back to the h limit, a formula for f prime of x is limit as h goes to 0, right, of f of x plus h minus f of x divided by h. Now this time, you see, I wouldn't want to use the limit that I'm about to underline in orange for the last thing I wrote. Why? You see why? Like here, x is playing the role that a did in our original definitions, right? Like here, x is the value at which we're calculating the derivative, whereas up here, x is a limiting variable. So the role that x is playing is different here and here. But anyway, going back to your question, what's dy dx? Well, dy dx is exactly this. It's what it is in words is it's the instantaneous rate of change of y with respect to x. All right? Instantaneous rate of change of y with respect to x. It's also the slope of y equals f of x at x. So, like, this is giving us the slope of the tangent line. I don't know if does that answer your question? I know. So, I looked over you guys, your mission 3, and I see that there's a confusion in terms of like what the instructions mean, right? So I think I should work an example to try to explain the difference in like what was asked versus what you guys did, and because we need to, I've turned the monitor around to the front, and I go to the back to see the monitor because I'm an idiot. So let's look at an example. So example, calculate derivative with respect to x of, let's say, 3x plus 2 from the limit definition of derivative. All right. Another way I could here's before I even do that. Another way I could state that same question, I could be like, let f of x equal to 3x plus 2 find f prime of x from limit-based definition. All right? So what would we do? We would use the limit-based definition, right? F prime of x, limit as h goes to 0, of f of x plus h minus f of x divided by h, right? What happens?
So what's the definition for like the
F of a plus h?
Yes, what is that definition?
It's the same one. All the difference is that I've used the letter a instead of the letter x.
Oh, no, so you just, okay, so you just use that one.
Yeah, I mean, cross a output x here, it's the same thing, right?
And I just want to make sure we use both.
I mean, they are the same definition. It's just a question of are we at x or are we at a? You know, I'm supposing we're at x. X is the fixed but arbitrary point we're calculating the derivative of the function at. Now, for this function, we have to evaluate what is f of x plus h, right? That's 3 times x plus h, right? Plus 2 minus what? Parentheses, 3x plus 2. What happens? We've got 3x plus 3h plus 2 minus 3x minus 2, right? So what cancels? Lots of stuff cancels, right? The 3x cancels with minus 3x. The 2 cancels with minus 2. And what are we left with? We're left with 3h over h, right? So that is the limit as h goes to 0 of 3. And then by properties of limits, that's equal to 3. So this would be how to calculate the derivative of 3x plus 2 from the definition, from the limiting definition. All right? So in your mission 3, I had some questions like that. Calculate the limit of the function using the limiting definition. But what I saw you guys do was something like this. So your solution was this. d dx of 3x plus 2 is, well, that's 3 times dx dx, right? Plus d dx. I mean, you didn't have all this maybe written out, but this is something like this, analogous to this would be your solution. And then, so the derivative with respect to x of 2 is 0, because it's a constant, right? This is 0, and this guy is 1. So the answer is 3. So what's wrong with my solution number 2? There's nothing wrong with it if the instructions were different, right? If the instructions it's just said calculate the derivative, I shouldn't take off points, right? But if the instructions say calculate the derivative from the limit definition, I've not followed instructions, right? See the problem? That's all. That's the problem. Now, so this is a correct solution, but it just hasn't followed the instructions. It's correct if we can remove use the definition to calculate the derivative instructions. But once those instructions are stated, then I have to grade the problem according to those instructions, you know? So understanding the definition understanding the derivative from the definition of limit is part of the course, you know? So how many of you guys had calculus in high school? Anybody had calculus in high school? No? How many of you had a tutor help you with mission 3? Anybody? So did the tutor happen to tell you, like, the so I saw a quotient rule in the solution. Did it?
I ain't even gonna lie, that wasn't a tutor. I just needed somebody to help me get it done, so I couldn't get it done. Didn't know how to do it.
I see. Well, okay. I was going to say the one thing I worry about with tutors sometimes is like tutors don't know where we are in the course, and so if a tutor doesn't know better, they might say, well, this is a quotient of functions, so we should use the quotient rule, right? But the thing is, we don't know the quotient rule yet. We don't know the product rule yet, right? Like, so like test 1, the only things you should be using on test 1 are like power rule. Let me write it out. These are the things we know about. So things we know at this point. So suppose for a moment that we don't have we're not bound by the instructions to calculate from the limit from the definition, right? Suppose I take the gloves off and you're allowed to use the tools that we have developed. What are tools that we have developed? We've developed number 1, derivative with respect to x of x to the power n is n times x to the n minus 1, right? So we have that to work with. Great. 2, we know that the derivative of a sum is the sum of the derivatives, all right? And you can do that for more than 2 things as well, right? I mean, it's still true if there's 3 things added together, right? This is a property, additive property of the derivative, we know that. And we can also pull out a constant. So these are 3 basic tools we have. The other thing that we know, really 3 more things. We know that the derivative with respect to x of e to the x is e to the x, right? We got that one. We have the derivative with respect to x of cosine x is minus sine x. And 6, we have that the derivative with respect to x of sine x is cosine x. So that's pretty much it for us at the moment. This is what we know of differentiation at this point in the course, if we're going to use just laws of differentiation. Now, after test 1 is done, then we'll talk about the product rule, the quotient rule, the chain rule, and we'll be able to differentiate many, many more things. But at the moment, this is all you're responsible for in terms of like just straight differentiation. Now, rule number 1 looks like a lot of different things for different cases of n, right? Like this is true for n in the real numbers, actually. So it's true for you know, for integers, positive integers, but it's also true for like negative powers. And one of the examples we did was like square root, remember? So let me just expand on one here for a second. How does 1 work? So how about n equals to 0? What's that look like? That's 1, right? X to the 0 is 1. So that's 0 times x, right? To the whatever power. So that's 0. So you could think about this n equals 0 as kind of a special case. It's the derivative of the constant 1 is 0, right? So n equals 1, we work that one out from the limit. d dx of x, that's 1 times x to the 1 minus 1, which is what? 1 times x to the 0 is 1, so that's 1, right? In other words, we have that dx equals to 1. How about n equals to a half? How does that work? So we do 1/2 x to the 1/2 minus 1, right?
Okay, so you bring the 1/2 down.
Mm-hmm.
So then it's behind x.
Yep. Yeah, this is the power rule. It's the power times x to the power minus 1. That's how we differentiate x to the n with the power rule, right? If we were to calculate the derivative from the definition, then we would be faced with an annoying algebra calculation, right? This is 1/2 x to the minus 1/2, right? What's 1? So you could leave it like that, right? But typically I find it's useful to write that answer as 1/2 times x to the 1/2, which is otherwise known as 1/2 times the square root of x, right? So we proved this in a previous day using the limit definition. We proved that the derivative with respect to x of the square root of x is in fact 1/2 the square root of x. Where did I take the negative? Well, this is a law of exponents, right? If I have a negative exponent upstairs, then I bring it downstairs, it makes it positive, right? So what if we, here, let me give you guys something else, something harder. Well, I don't know if it's harder, but something different. What if we're going to differentiate, say, x over the cube root of x? How would you do it? Plug in 1/3. Well, see, the problem is here is that it's not in the right format yet, right? Like, we need x to the power n. We don't have that. We have a quotient. I need this to be x to the power n for some n. How can I make that? How can I do algebra here to rewrite that as x to a power n? This is what, x over x to the 1/3, right? Which is x to the 1 times x to the what? Minus 1/3, right? Yeah, x at the numerator is the first x, right? Yeah. This guy goes to that one, and this one puts that factor there, indeed. And then what happens? This is x to the what? 1 minus 1/3, right? What's 1 plus minus 1/3, which is 2/3, right? So this is x to the 2/3. So now we can do the problem, right? We have d dx of x to the 2/3. Now I have it in the right format to apply the power rule. See, I can't apply the power rule. We've got to be really picky about pattern matching in here. If it doesn't match the pattern that it's supposed to, we can't apply the rule. Like, you can't just... Other thing I saw you guys do was like... And I'm not sure which one of you did this, but I saw it in somebody's paper. Like, basically, they applied the rule for the derivative on the top, and they applied the rule for the derivative on the bottom, and they just divided them. Like, that's not a thing. It's more complicated than that. It's that quotient rule that you used. But we don't know that yet, so we have to do algebra. Actually, it's never the case that this isn't the way we're doing it right now, isn't the right way to do it. Like, even once we know the quotient rule, applying the quotient rule here is not the right path. It is always the right path to simplify algebraically when you can, and then differentiate, almost without question. So what do I do now? Bring the 2/3 down. All right. So I apply the power rule, right? 2/3 x to the what? 2/3 minus 1. Negative 1/3, right? So I have 2/3 x to the negative 1/3. And that's not a bad answer. I mean, you could put a box around that and be done with it. But suppose I want to write my answer using radicals, right? This would be also equal to, I mean, I think you guys need some practice on this, right? 2/3 times x to the 1/3. We could write it that way, right? Right, yeah, 2/3, not the square root, though, the what? The cube root. So we write a 3 here, x like that, so yeah. But again, to be fair, I really probably would not, depending on, unless I wrote the question, the instructions rather precisely, if I say leave your answer in terms of radicals, then the yellow boxed answer would be the right answer, right? If I just say differentiate, no need to simplify, then the red answer would be fine. Yeah. But yeah, this is the power rule. Should we do another? Probably should do another. How about this? d dx of x over x to the 4th. So like first order of business, we have to write it as x to the power n. So this is x to the what power? is everybody? I said I was going to have a quiz today, possibly. Are just 3 people taking this class now? Goodness gracious, this is not a good pattern. No, no. So maybe I should give you guys some homework on like laws of exponents. That would be helpful. X to the negative third. Yep. Right. Now we can apply the power rule, right? So -3. I think the power rule application is actually the easiest thing going on here. The hard part is applying laws of algebra to put it into the right form so that you know how to do the derivative law. So -3 minus 1, which of course is -4, right? Which we could write as -3 over x to the power 4. So would it be helpful for you guys for me to go through there's I think, problem everybody got wrong on mission 3. Let's see here. See, so like problem 47, I guess I left myself open to attack. Like my intention with problem 47, so like at some point in mission, was it mission 4? At some point I have like a statement on the mission that I say, okay, past year, you feel free to use the power rule and so forth. I think that's in mission 4 actually. So my intention was actually for you guys to use the definition from the derivative, definition from the limit for problems like, for pretty much every problem before, sorry, I'm trying to find where I put that banner in your homework. All right, so like past problem 58, problems 59, 60, 61, 62, 63, 64, there I would encourage, in fact, welcome, in fact, hope that you would use things we know for like problems 59 through 64, right? But before that point, I have tried to put instructions, and I wasn't always successful here, I guess. Well, for problem 54, for example, I have, g of x is this, f of x is that, h of x is their composite. Calculate the following from the limit definition of derivative, right? Problem 53, calculate the derivative from the limit law type calculations. So it should be clear in problem 53 and 54, you need to use the limit law definition for derivative to calculate those. So your homework, mission 4 is a mix. The start of mission 4, all of the calculations are from the limit definition of derivative, right? The last about 5 problems, you can use the things we know, the power rule and the linearity to calculate the derivative, right? In mission 3, I neglected, so what I'm saying is, like, I'm not going to, well, honestly, since you guys tried something, I'm going to give you full credit here because, well, I don't see the point in taking off tons of points here. I think everybody tried. But you're a ways away from what's right in mission 3, unfortunately. And that's pretty much everybody, all right? So I posted a solution. I would encourage you guys to try to work through that before Friday. It would be wise. Certainly we can talk about that Wednesday once you have a chance to look at it. Mission 3 solution is already posted, right? It's in course content, so you can look at it. I'm going to give you your mission 3 back here pretty soon. How about now? So I haven't even marked. I mean, I was looking at it, and I came to the realization that it would take me it would take me a long time to explain everything that was wrong about what's here. So rather than bloody the page with all of my red pen, I'm just going to let you guys have these back. And I do know that you did them. I will, you will get full credit for these, because I do think everyone here has made a pretty serious effort in doing it. It's just things weren't quite in place yet at that point. Let's actually look at the solution that was intended, though, for one of those. Excuse me. If I can find my mission 3 now that I've given you back yours. Let's see here. All right, I'll start with the most problematic one. All right. So this was problem 48. I said A is not equal to 2. Calculate f prime of A for f of x equal to x over 3x minus 6. Now, pretty much here, there is really no choice but to use the limit definition at this point, because we don't have the quotient rule to use. So like our only choice really is to use the limit definition. And the solution I have in my notes is using the x approaches A. I'm going to try the h one here and see how it goes. So what I'm writing on the board will be different than what's posted, the posted solution. So you can compare and contrast to how this goes. Now we're supposed to calculate f prime of A. So that should be f of A plus h minus f of A divided by h, right? How's that go for this formula? So I'll write the 1 over h out front just to get it out of the way. And then I'm going to write f of A plus h here. That would be A plus h over 3 times A plus h minus 6 minus A over 3A minus 6. So I think the first thing I'll do is factor a 3 out just to get it out of the way. There's a 3 everywhere, right? So I can factor a 3 out. This doesn't do too much, but here's a, slight improvement. A plus h over 2a, over a plus h minus 2 minus a over a minus 2. And then I can't just plug in h equal to 0, right? Because if I do, I get division by 0, right? Yeah, there's division by 0 right here. Mm-hmm. Why do we have to divide? What do you mean? What's in the big parentheses is f of a plus h minus f of a. Yeah, when I have big expressions like this, because I mean, I could write a giant fraction with fractions on top, or I have the option of just multiplying by 1 over h. It's just easier to write and make big details big. Because f of x is x over 3x minus 6. So, yeah. It's nothing more than this and that are playing the role of x in this formula here, just like that. But we do have to think through it. I mean, that's one of the hard steps in this problem, is making that substitution of a plus h for x if you choose this path. If you use the x and a formalism, it's like you look at the solution later, you'll see that if you use the limit as x goes to a formula, it has its own set of like annoying aspects. Like, I think the algebra is a little bit easier here than what I have in my solution. My opinion. We'll see. So I can make a common denominator, right? Make a common denominator, cross multiply essentially. And what happens? I get a plus h times a minus 2 minus a times a plus h minus 2 divided by a plus h minus 2 times a minus 2. Now, multiply out that numerator, what do we got? Oh, maybe, yeah, okay. So a squared plus HA minus 2a minus 2h minus a squared minus AH or HA plus 2a. Denominator stays the same, right? Some stuff should cancel, right? Like the a squareds cancel. 2a. So generically speaking, like when I do this kind of problem, what I'm looking for is in the algebra, as I expand f of a plus h, what usually happens is the formula for f of a appears in that, plus other stuff. But the part of the formula f of a plus h, which is f of a, will cancel with f of a. That's what's happening right now. Like, that's a little bit of a lie, but it's right. But yeah, this, oh, and the HAs cancel. Cool. So all that's left is just that lonely minus 2h, right? Which I would point out, we can reduce this and that, right? So after we make all those reductions, we're just left with an h upstairs times minus 2. So in short, limit h goes to 0 of minus 2 over 3 times the denominator function. And at this point, we don't have 0 over 0 or 0 times infinity anymore. Yep. The 3 is multiplying the whole of the denominator. Yes. Yes. And that minus 2 is from this one. So plug in h equal to 0, we get what? We get minus 2 over 3 times a minus 2 squared. There you go. That was problem 48. Again, if you look at my notes, if you look at the solution that I posted, you'll see that my algebra is quite, oh, come on. Oh, I was so careful to leave the camera over there. Moron. Well, at least everyone's here today, so they saw it. Wait a minute. Oh, they weren't here. Let's see here. There's the top of it. Zoom in a little bit more. All right, let me get a little bit more mileage out of this example here while we're at it. Now, this was not in your homework, but I think it would be useful for us to, first of all, change notation, see what the result looks like if we write it in terms of x, right? And then let's also find the equation to the tangent line of this function. All right, so like if y equals to x over 3x minus 6, all right, then we have shown that dy dx is actually equal to minus 2 over 3 times x minus 2 squared. So here I'm changing the letter a to the letter x to denote like where the derivative is taken. But if it's true for an arbitrary a, we can replace the a with x just the same, and that is also what's called the derivative function. Like this is the formula for the derivative function. If
So right now we just made y equal x.
just to go back to your question.
So that answers it. Y equals something, and then we're trying to find derivative of it. We have to use dy dx.
Yeah, I mean, that's an option. So, I mean, this is the thing is, when the problem has stated y equals f of x, you could either call it dy dx, you could call it f prime of x, you could even call it d dx of f of x.
Oh, okay. So this is just one of the ways you could solve this problem.
One of the notations we could use to express the answer. But this problem, I specifically asked you to calculate f prime of a from the limit definition. So like I really should do this. This is the natural answer to the question as it's stated. But if I said y is equal to that, you know, then this. I mean, for what it's worth, if I said that Pac-Man was equal to x over, you know, 3x minus 6, I mean, I could be weirder. I could say Pac-Man is equal to Ghost over 3 times Ghost minus 6, and then it would not be wrong to say that the derivative of Pac-Man with respect to Ghost is equal to minus 2 over 3 times the product of Ghost minus 2 quantity squared. It's all the same math, it's just different letters. Okay, so find the equation of the tangent line to y equals to x over 3x minus 6 at point with x equals to 2. That was not asked in the homework, but I think it's an interesting problem to look at, right? Well, I didn't even ask you to graph it. I just said find the equation of it. So the equation of the tangent line we defined is y is equal to f of 2, at 2, f of 2 plus f prime of 2 times x minus 2. Right, but careful, we don't put f prime of x there. We have to plug in 2 into the formula we found.
Why would you put x minus 2 in there?
This is to get, this gives me a line through 2, comma f of 2 with slope f prime of 2, and that's the tangent line.
So say if it was 3, you would just write x minus 3?
Yeah, and I put a 3 here and here.
Okay.
Yeah. So like if you go back in the first day I defined derivative, I also defined tangent line in that day. And we said definition of a tangent line is f of a plus f prime of a times x minus a. That gives us the equation of the tangent line at a, provided the derivative exists, right? There are functions where the derivative don't exist at the point, like the absolute value function at 0. Let me erase my Pac-Man nonsense. What's that? So,
So you didn't work out the y equals x over 3x minus 6. So you would have gotten the same answer, right, as that one?
that's right. Yeah, if I change from a to x, it's not going to change the pattern. No.
You could have still used, like, say I could have still used f of a plus h, but I don't.
Yeah, we could have just, in fact, like if you want to, you could go through here and just go, x.
Okay.
I wouldn't advise doing this, but since you got me started, I'm not going to.
I get what you mean.
It's the same algebra. So we define a function by its formula, right? But the formula really is just a means to communicate a pattern, right? A formula a function is a machine in some sense that takes an input and does something to it and increases an output, right? It doesn't matter if you call that input x or if you call it a, it's still the same machine, So can you guys find me the equation of the tangent line? That's how we do it. That's a guide, but what is the actual formula? I have y equals to, what's f of 2 here? F of 2 is 0? Oh, that's the worst possible choice. Oh my goodness, that is, of all the infinitely many real numbers I could have,
Really, 0?
it's worse than 0. It's not defined. 0 is it's the one thing I'm not allowed to do.
Change to 3.
I'm in the mathematical Garden of Eden, and I have eaten the forbidden fruit. That's what happened. This is the one fruit of which I cannot eat. 2. No, anything but 2. Pick a number, any number, just not 2. 3, okay. See, I can't do 2 because there's a vertical asymptote in the function at 2. There we go. Now I can do that. F of 3. Okay, so f of 3, what's that equal to? 3 over 3 times 3 minus 6, whatever that is. Yeah, plug it in. I can't do math. Look at this. There's no parentheses. Parentheses is totally bogus. 9 minus 6, which is 3. So f of 3 happens to be 1. Yeah, it is a good number. That's right. F prime of 3 is, well, what's the formula? minus 2 over 3 times a minus 2. Well, a is 3 here, right? 3 minus 2 quantity squared. Three minus 2 is that number that you like, right? It's 1. So the derivative here at 3 is minus 2/3. So therefore, y equals to 1 minus 2/3 x minus 3. This right here is the equation of tangent line is there it is. Now, if you want me to graph it, I mean, we could, right? How would you graph x over 3x minus 6 anyway? Do you know? Now, this that I'm telling you right now is really pre-calculus, right? But what I would do is I would maybe, I mean, there's various ways, but you could use long division. So this remainder is 6. So this y is actually equal to 3 I'm sorry, just a second here, guys. It feels wrong. Oh, I've reversed the roles. I'm long dividing wrong. It's like, this is not right. I'm supposed to do x divided by 3x minus 6, right? The number you're dividing by goes over here. The thing you're dividing into goes over there, right? If I had 500 over 17, no one would be confused, right? You'd be like, oh, well, obviously you put the 500 here and the 17 here, right? I mean, that's not. It's just when I have polynomials, I sometimes lose track of what I should do. So I have to put 1/3 up here to get this to be x minus 2, and that gives me a 2 for my remainder. So this is actually not 3, but 1/3 plus 2 over 3x minus 6, right? And we can factor 3 out of that. So it's actually 2 over 3 over x minus 2. And so that I can graph, because what we're looking at is something that has a horizontal asymptote of like 1/3. A vertical asymptote at 2. Right? And otherwise, it's like a reciprocal function. So what is it at 0? At 0, this thing's 0. So it's something like this. That's the graph. And we also happen to know that at 3, which would be right about here, right, that point would be 3, 1, the point of tangency for our tangent line, right there, and we could graph it. It's a line with negative slope. There you go, that's the tangent line. Something like that. So of course the orange is y equals f of x. in the blue, if you want me to give a name for it, it's y equals the linearization of f at 3 of x. The linearization of the function at the tangent, at the point of tangency, is the function whose graph is the tangent line, as we talked about in the lab, like the first problem in the lab last Friday. Hey, there were more students here in the lab. I should just say every class is a lab. Then they'd be here. That was my mistake. All right, from now on, every class is a lab. We're going to meet in this room, and I'm going to lecture, but we're going to call it a lab. And that way everyone will come. You think it'll work? It might. Should I bring donuts? If I brought every day's pizza day, would that help? You'd come? But you'd come anyway. You never know. You're going to stop coming just so I start giving pizza every day? It's a strategy. I don't recommend it, though. All right, so listen, limits are something we have to, they're part of the course. They're something you need to learn how to do. But at the same time, I hope you're starting to understand that if we can get away with not doing them, then it's preferred, right? So I'll let you look at the solution to number 49. It's a page of algebra to calculate that derivative from the limit, Let's look at another example. Suppose we had f of x equal to x cubed plus the cosine of x, all right, minus 8. So I want you to find f prime of x and f prime prime of x, then give equation of tangent line at x equals to, let's say, pi over 2. Did I say example? I meant quiz. Let's make this a quiz. So get yourself a piece of paper. All right. This is quiz 1. So that is your quiz 1. So if you're not in class right now, I need the answer to this before the next class, all right? Or at the start of next class, you can turn this in. Thanks.